Hey, Aaron, good morning. And Alessia, good morning. Alessandra and Tim H, good morning. And Timothy P and Ayala, good morning. They're coming quick now. Matthias, Corsin, Malta, good morning. Allie, good morning. Stella, good morning. Isabella, good morning. And Isaiah, good morning. Corey, good morning. Inessa, good morning. Clara, good morning. Leo, good morning. I'm getting quicker at this. Sina and Kiara, good morning. Zach, Linus, and Ingrid, good morning. Okay, while I'm pausing here, what's up? So today we're talking about more or less a helium nucleus, and it comes out of the nucleus and fires off. So, and I'm getting a message, my connection's not real stable, so if you lose me, don't worry, I'll come back. But let's keep going until I get cut off. Hopefully I won't get cut off. Hello, good morning, Charlotte. Okay, maybe I've stabilized now. Hope so. So we did number one yesterday. We said that in general, radiation is something radiating out from the nucleus. And Aslan is here. Good morning, Aslan. Super. Okay, I'll take a check of others in a moment. And yes, good. Sophie's here too. Good. Welcome, Sophie. So let's make a spot here for number two. Some of you knew this already. We did alpha radiation. And the second one, I'll turn my camera in a sec here. I'll turn it right now. The second one is called beta radiation. And I think I gave you the symbol. It's like a German Etset or the Greek letter beta. Let's see who else is here. Hold on, let me mark a couple others in before we continue. I've got Devante and Liam. Okay, Liam, go ahead and watch the rest of it on the video. But thank you for checking in. Devante and Liam. Good. Okay. Back to beta. Beta is, frankly, my friends, weird. Okay? So I'm going to try and explain what happens. Turns out I haven't told you everything about the atom. Big surprise. There are particles that make up the neutrons and protons in the middle of the atom. I can break them up into subatomic particles, which are called quarks. Those you don't need to worry about unless you want to take more physics in 11th, 12th grade. But for now, the one thing you do need to know about is I can make a proton out of adding together a neutron. Now say, okay, sorry, start again. I'm sleeping. Start again. I can make a neutron out of a proton plus an electron. Bizarre, huh? So they actually join together and create one thing. If you think about the charge, it kind of makes sense, right? These are positive, these are negative, and these are neutral. Oh, so electrically it makes sense, even though the particle thing's a little weird. Let me check a couple more of you. Thank you for joining me. I've got Abram and I've got Lauren. Welcome you too. So, what does this have to do with beta? Well, this is more or less what's happening with beta. And Amelie, I got you. Okay. This is more or less what's going on with beta. So with beta, I don't know if you ever saw old movies with Superman. Superman would go into a phone booth, spin around, and become Superman. Well, he would go in as Clark Kent, and he would spin around and become Superman. That's kind of what happens here. A neutron goes into a phone booth, if you like, spins around and becomes a proton. But at the very same time, to become a proton, an electron has to shoot off. The electron, folks, is the beta particle. So let's say that in words. So beta radiation is a neutron in the nucleus changes into a proton, comma, and an electron leaves the nucleus. So it fires off somewhere, usually far away. If I could spell this morning, come on, nucleus. And the electron, folks, that's the that's the beta particle. So beta particle is just an electron. So it's weird. It's weird. To show that as a little diagram, so here's my proton. Here's my proton. And so what happens is it becomes let's do that in green. It becomes a neutron. And remember, they have about the same mass because electrons really don't have a lot of mass, okay? So this is, and at the same time, an electron goes flying off. There goes the electron. I know it's a lot smaller, but we're just going to have that thing fire off, okay? Oh, that looks like it's changing into it. Let's just leave it like that, okay? Okay, let's write some symbols here. So the symbol for proton is P+. Not a big surprise. Maybe I told you that. I don't know. The symbol for neutron is N, small n, with a 0 because it's got a neutral charge. Makes sense, right? The symbol for an electron is E, and I can do a couple different things. I can do a -1 up here, or I can do a -1 down here as the charge. Sometimes you'll see it like that, okay? So I got a minus at the top with the lower left-hand corner. I can do a -1 as well. Not so important. Okay, how does it turn into a proton? Kiara, very carefully, the better question might be why. Turns out that the protons and neutrons are made of even smaller stuff called quarks. Okay, so it's not a question of just how does it do it, but why does it change it? Why does it change? We're going to find out. It needs to become stable. Anything that's going to do beta radiation is not a stable nucleus. And we're going to tell you in the next week or so when things are unstable. You're not going to have to know that, but in general, what sort of atoms are unstable? Also, I'll just say bigger ones are pretty unstable. Okay, so other questions from Sophie. Does the beta particle electron leave the atom completely? Yes, generally it does, Sophie. So this electron doesn't join the atom, doesn't join one of the shells of electrons. It goes flying off here. Maybe I should show that. Ready? Away it goes. It's out of there. Okay? So that electron generally leaves the atom. Thank you for asking. Good question, Sophie. Isabella, doesn't the neutron turn into the proton? It does, but to do so, its other part, the neutron, it's composed of a proton and electron. The electron has to fire off to become. Wait a minute. Isabella, thank you. She caught my mistake. I got so carried away, I screwed these up. Okay, change. All right, so start again. Apologies. Thank you, Isabella. Extra points for you. So this sucker is my neutron and 0, and that breaks up, as I set up above, into a proton. My gosh, it's hard to get good teachers. Right, and part of becoming a proton is the electron gets fired off, as I said a moment ago. Much obliged to Isabella for catching my mistake. Good. We're going to do a reaction now. Any other questions before we do a reaction? I'm going to hold this a little closer in case you can't see some of that stuff. You see all that in there? Right? My high-tech studio here. Okay. Because I'm going to erase it in just a sec, but I lost my marker. And there it is. And how does this look like on paper? That's what we're going to do now. Michael, thank you for joining us. Checkaroonie. Michael, you have to look at the video because I got to erase this. And you can look up beta from the video later. All right, so let's do an example. Once again, like yesterday, you need a periodic table, and you'll need one for the homework that I'm going to assign in the next day or so as well, okay? Periodic table, so find one. Should be one at the back of your planner. You can find one on the internet, wherever, but you'll need that for this and for the homework that you'll assign at some point. Okay, and that having been said, let me grab mine, which is right behind you. I'm going to pick something and to have a beta, to have it undergo beta radiation. Okay, so I'll just say calcium, I want to say 42. So if calcium 42 undergoes beta radiation. Okay, calcium 42 is an isotope. And the 42 is, when I say it this way, the 42 is the mass number. Remember what that is? Mass number. It's the number of He plus Hm. So who remembers from last time? What was the mass number? Please type it in, somebody, real quick. just as an aside. So when I say calcium 42, the 42 is the number of what? It's the mass number from last time. So what was that? Then we'll continue. Almost. There, a couple of you got it. So Sophie has it, as does Alessandra and Aaron, Devante, and others. So it's a number of protons and neutrons. That's why it makes up the mass, okay? So protons and neutrons. So I know this isotope is radioactive. I know that because I've been in the business a long time. You don't have to know that. I'll have to tell you that. So now let's write a reaction, okay? So a nuclear reaction. That's my point. So here we go. We're going to go Ca, the symbol for calcium. The 42 goes up here. Remember that? What goes down below? What goes right in this spot? Who can tell me? And tell me the number if you know it as well. Yes, you'll have to use your periodic table. What goes down there? 20. No, not 21. No. Lauren has it, 20. So it's the number of protons. Thanks, Lauren. Called the atomic number. And for Ca, that's 20. If I can see you, right? Yeah. So add a 20 down here. Now, again, we're not going to worry about the charge or anything. So I'm just going to say, okay, that's going to undergo beta. I'm going to use the B symbol for beta, but we know it's an electron. Doesn't matter. Plus, okay, what's left? Okay, now it becomes tricky. You ready? Ooh, a lot of you knew that. Thanks to Ingrid, Leo, and others as well. I had a neutron become a proton. So what happens to my number of protons down here? What is it now? It's no longer 20. So who's following? What will my number of protons be now? My atomic number. It's no longer 20. You got it. Thank you very much, Isabella, Kiara, and others. Lots of it. Corey, thank you very much. It is indeed 21. Now it's got an extra proton. Isn't that weird? It's changed identities. It's no longer the same atom. Does it really happen? Yeah, all the time. So I can change one atom into another. Well, all right, they change themselves if they're unstable. Thanks, everybody, for participating. Good. I got it from Aaron and Allie and others. Good. Okay, so that's 21. Now, the top number is a little weirder. The top number, remember, was the number of protons plus neutrons, right? What happens to the top number? What happens to the top number? Good. Isabella and Sophie got it. What happens to it? Nothing. It's the number of protons plus neutrons. So if I have a proton changed to a neutron, it's still counted in that number. Right, everybody? It stays the same. It's still 42. Isn't that weird? But now it's no longer Ca. Can somebody look up and tell me who it is now? Who is it? Who's number 21, please? Who has it become? Oh, some of you got it already. Thank you, Kiara. Good. It is scandium. Scandium. So Sc. Can you guess where they discovered scandium? Just for grins? Where did they discover scandium? Yeah, it's number 21. That's how we know it's scandium. Check on your periodic table. It won't be potassium. It's going to be the other way, right? It's going to be 21, not 19. Nobody knows Scandinavia, right? Makes sense, right? There you go. Isabella knew it. Okay, so did Aslan. Okay, nice. Okay, that's the second type of radiation. Beta is the most weird, okay? The third type is a little bit less weird. So let's do the third type. So the third type is called gamma. Gamma radiation. Here's a story with gamma. Have you ever sat down in a chair and you're not real comfortable? What do? Don't you scoot a little bit and get more comfortable? That's what gamma is. The protons and neutrons in the nucleus move a little bit to a new configuration. And that new configuration is lower energy. Okay, Felix, you're there, but you're mighty late. So you're going to have to see the rest on a video because you missed a lot of stuff. Okay. Alessia, I have no idea what you're talking about. Sorry. Yulia, same thing. You're late, so you're going to have to see the rest of the video. Send me your notes. Okay, but at least you're here. So let's do gamma. And maybe I'll put a definition first. So the protons and neutrons shift like you do in your chair, shift to a what we call a lower energy position. When they do that, this releases some energy. In the form of light. So gamma is actually a type of light that comes out of the nucleus. Okay, let's see if you got questions before I go back here and continue. Oh, the Hulk knives. Thank you. I missed that totally, Alessia. Yes. Yeah, gamma was what they used to use in the old Hulk TV show, right? Or movie or whatever, right? Got it. Got it. Kiara, not like the metals that shine, because metals only shine if I turn on a light and then it takes in and gives off the energy again. If I'm doing gamma, I can shine at night or day or anytime because the energy comes from me inside. So it's me when the particles. Hey, here's the protons and neutrons. Okay, so if they shift around and become more comfortable, boom, some light fires off, and that light we can't see. It's not in the visible light spectrum, but it's called gamma light or gamma radiation. Okay, so this light. The light is gamma radiation, and it can be harmful if we get a lot of it. So light as gamma, you can say gamma rays or gamma radiation, however you want to say it. But we can't see it. It's invisible. It doesn't mean it's not strong, but we can't see it. Invisible to us. You can't see it. But it can do either good or bad things depending on how it's used. Okay? Okay, we ready for an equation? Let me see if there's any other gamma questions before you all hulk out on me. Okay. Like glitter. Not really like glitter, because glitter also needs light coming from somewhere else to shine off of it. This is not shining off the thing. This is the light coming from the actual nucleus. So it's from here going out. It's not reflected off like for metals or something, okay? Remember, metals, the light comes in, moves the electrons, and then the electrons give off light again. That's not what happens here. Here it's from the inside nucleus, boom, it gives off light when the protons and neutrons shift to a lower energy spot. What would it look like if you could see it? Devante, it would be a ray with a very, very, very short wavelength. So short that it would be like the size of an atom long. That's how long the waves. If I make a wave like this, right? That's like maybe 10 centimeters long, okay? These would be like the length of an atom long. So if you could see it, Devante, it'd be really, 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 really super small, but we can't see that small. Would it be green in the movie? Nah, it wouldn't be any color because we can't see it. So it's not in the color part of the spectrum. So alas, the only thing you could do is measure it on a Geiger counter, which I'll show you how to use maybe in a separate video. Okay, Geiger counters. What about things that glow in the dark? Well, I don't know. Lots of things glow in the dark, so I can't answer that exactly, Leslie. Okay, let's do a reaction. So here we go. Let's do thorium. So 90 thorium. Thorium. I don't know. 234 maybe? Sure. 234 undergoes. Does goes have an E in it? I think it does. Undergoes gamma radiation. So the reaction. Okay, thorium is TH. So you can look for that on your periodic tables. And I told you it's 234. That's the mass numbers. That's going to go up here, 234. What's the bottom number for thorium? Somebody find it for us. Does all natural light come from gamma radiation? No, very little of it, Sophie. Most natural light comes from our sun, right? And we'll learn how that's given up. But more or less, it's a sideline from the heat that is available when the sun undergoes fusion. And we'll study that later, probably in about a month, fusion. And it is 90. Thank you, Isabella. So it's got 90 protons, TH. That's the atomic number that goes down below here. Okay, here we go. Gives off. Okay, the symbol for gamma looks like this. It's like a fish swimming down. Okay, that's the gamma symbol. It's the Greek letter gamma. Looks about like that. I'm not the best drawer of Greek letters, but that's more or less what you want to write. So a fish swimming straight down, that's gamma. And what happens to the mass and the atomic numbers here, gang? What happens to the mass and the atomic numbers, given what I said down here? No. And short answer, Alessia, is no gamma radiation, no gamma light is visible to the human eye. What we can see is like purple through red. Okay, we can't see ultraviolet, we can't see X-rays, we can't see radio waves. Those are all types of light. Gamma is a type of light. We can't see it. So how would it look like? Well, I don't know. We can't see it, so I don't really know. Okay, and the right answer is nothing. Thank you, Aslan, Kiara, Sophie, Ingrid, and others. So the numbers stay the same because all they're doing is shifting around. So guess what? We got 234 and 90, and it's still thorium. You might say, but Mr. Weiss, that means nothing's happening. No, it means the nuclear particles have shifted around a little bit. What has happened? Some gamma's given off. Get out of the way. All right. That is important if it's something that you've got to have go through your skin or whatever. You know what I'm saying? So Nothing happens to the numbers or the identity of the element. It's still thorium. Okay, so that's up with gamma. That's right. The particles just switch around a little bit. Let's see exactly. Okay. Leo has an interesting comment. The charge becomes higher because the electrons leave the atom. There's no electrons leaving the atom here. That happened when I had beta. For this, the only thing leaving the atom, Leo, is some light. So it's not affecting the charge at all. It's still got the same charge, probably neutral, if I don't tell you anything else. Okay, any other questions? Yeah. What is useful for this example? You want to know what it's useful for? I'll give you a good example. If you've got cancer, and we'll talk about how to treat this later, but they can use a type of cobalt that gives off gamma radiation, and they aim the cobalt sample at your tumor, and they can destroy cancer tumors with gamma. So gamma has some positive uses as well as some potential harm. If it gets into areas that you don't want to harm, it can harm the skin and the bones and the flesh, okay? But it can be used as a surgical tool, gamma radiation. So that's why we need to know about it. Okay, exactly. Got it. Thanks, Leo. Okay, so how does it affect the atom or molecule? Not really much. You're not going to really see a physical. It's not going to affect unless you're the boiling point or the melting point or anything like that. You won't see any change between here and here. It won't affect the physical properties any at all, as far as I know. It'll just give off some light. That's it. That's it. Good. Okay. Let's see how we're doing. We're doing okay. All right. So I need to then talk to you about the fact that these don't always happen just once. Yeah, gamma can kill people too. Exactly. Right, Michael. So gamma can be, if I get a lot of it, it can actually hurt you. Like if you're in a nuclear bomb, like folks in Japan were in World War II, that can kill you ultimately, or at least cause problems with your health. But it can also be used to kill cancer. So it's like a good bad thing. A lot of things in this world are good bad, right? Depends what you do with it. Okay, so we need to talk about this phrase, decay series. And what it means is this. Often, radioactive isotopes undergo decay in several steps until they become neutral. No, not neutral. Stable is the word I want. So as an example, okay? Let's make up a goofy example. Okay, so the element goophion, is that real? No. Okay, I'll call it goofium. Does an alpha, then a gamma, then an alpha, then alpha, then beta, then a gamma, then the product, it won't be goophium anymore, is stable. And it stops. Now, I'm just making this up, okay, off the top of my head, but that's a typical decay series. It undergoes a series of steps, series of radiations, okay, maybe an alpha, a gamma, an alpha, a beta. We think it's random, but the atom knows what it's doing, and it does the same decay series each time. If I have two different goophiums, they'll do the same thing if they're the same isotope, okay? And ultimately, then once you get to the stable product, it stops and it's done. But that's a decay series, okay? So it's a series of steps, a series of steps. But you got some questions, yeah? Let's see. No, Leo, it happens from within. So it gives off light, Leo, but only one time during gamma. So if he's back to gamma, they shift and they give off light once and it's done. But the light's not coming from anywhere else. It's coming from the movement of these to a more comfortable position, what we call a lower energy position. Okay. Yes, good. If an atom's stable, it won't decay. Thank you. Let me write that on here, Alessia. That's a good point. Won't decay. Now, look at your hand, look at your skin, look at yourself. Most of the atoms that make you up are stable. Aren't you glad? But a very few, even in us, a very few natural atoms undergo some sort of decay, some sort of radiation. Okay? It's just by luck. We're made of an unbelievable number of atoms, and a few of them are radioactive just by luck. Also, because we interact with our environment, and I may show you that in the video that I'll make for you about the Geiger counter. So that's kind of the deal. Okay? Now, I got to tell you what these are called. I'll just show that. Let's call it GF here. I'm going to make something up. GF. Let's say I got GF 421. And let's say it's number, oh gosh, I don't know. I'll make something silly. Let's say it's number 200 down here. Yes, I'm making up a new element. Okay, when it makes the next thing, whatever that is, this is called the, and I know it sounds sexist, but I don't know any other term. It's called the daughter particle. So, for example, the first one, let's see, goophium does an alpha, right? So I got to take 2 away from here, so I'm at 198. And I got to take 4 away from the top. I should ask you that, but I'm kind of in a hurry. So that'd be 417. And the daughter particle, and now I don't know what it is, 198, I got to make something else. We'll call it Mickey Mouseium, so MM. All right, I don't know. But anyway, that would be the daughter particle. And this one over here, the starting one could be called like the parent. Again, sorry if that sounds sexist. I don't know any other phrase that scientists use to describe it. So I got the parent and the daughter particle. But you know what? This could become a parent because I get another daughter particle here when I do the next step. So what did? I did an alpha. Now I'm going to do like a gamma. You know what I mean? So now I get a new daughter particle. So I'll get a series of daughter particles. Those in turn become parents, so to speak, and then they go and do another step and another until we get to something stable that won't decay anymore. That whole idea is a decay series. I'm sorry it's complicated, but that's the way it is. So some atoms do a lot of steps before they're stable. Some do not. Some do one. But I'll say most of the ones I know of do more than one step. Okay? decay? All right. Any other questions from you? Let me look and see what you're asking or saying in the chat. Thanks for your participation. You've all had a lot of good questions today about this. Yeah, I know it's complicated. But like I said, it's useful medicine, and it's not useful bombs, and we can talk about good and bad things that happen to the body later. No, Alessia, no. You can die of all sorts of things, but generally your atoms are not unstable, luckily. How does the decay of atoms affect us? Devante, the fact that I've got a few of my atoms decaying all the time in my body, luckily doesn't affect us at all. It's not enough to cause an internal cancer or anything like that. So the fact that we've got a few atoms that are undergoing decay or radiation, don't worry about it, folks. Your body's used to that. We've had that in the generations of people before us. So we've evolved with that. It's nothing that's going to harm you. So I'm not trying to freak you out, okay? It's part of being on Earth and being made of matter. A certain amount of matter is, by luck, radioactive, but it's a tiny, 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 tiny amount. 1 in a million, 1 in a billion atoms, maybe. Okay, so not very much at all. Oh, I'm sorry, I gotta blow my nose. Pardon me, studio break. Okay, there we go. All right, so yeah, luckily it does not, Devante, really affect us much. Okay, beta reaction, does the upper number never change? Or was it just this one reaction? Okay, Kiara, in beta, because the beta is the one that goes from being a neutron to a proton, if the top number is the number of neutrons and protons, it doesn't change. Okay, watch this. Let's say I got 4 neutrons, and to become a proton, I've got to take and shoot off an electron. Boop. But then now this thing is just a proton. So I still got 4 things, 4 neutrons and protons, even after the radiation occurs and the electron flies off. So the top number, if it was 4, it's going to remain 4. And that will always be the same. If it's 10, it's going to remain 10, whatever it happens to be for beta. So the top number, yes, Kiara, always stays the same. It wasn't just this example. Would eating bananas kill you from the radiation? Not that I know of, Michael. I don't know why. Why, especially bananas? Okay. Okay. Ute. Let's think of what else I want to tell you. Not that I've run out of stuff, believe me. There's a lot to do in the world. Let's start to answer this question. Why are some atoms unstable? Why? So now let's really get to what's happening, okay? Well, the short answer is they are not in the belt of stability. I didn't make that up. That's the actual name of it. And you might say, well, what the heck is that? Okay, I'm going to show you what that is. Belt of stability. Actually not. I see that I got 1 minute left. So you know what? I may show you that in the classroom. I can draw a graph, but I've got a really, really, really big actual belt of stability graph, which is cool to look at about once, but it's so big I can't really show you in my 1 meter studio here, okay? So I think I'll do a demo at school and record it as a YouTube and send it to all of you, okay? But for now, let's just say that if it's got about the same number of protons as neutrons and it's a small atom, it's stable. For example, helium has 2 protons and 2 neutrons in its nucleus. It's stable. Carbon has 6 protons and 6 neutrons. It's stable. You know what I'm saying? That one-to-one thing is true for small atoms. But bigger atoms, they end up needing more neutrons than protons. So the belt of stability is not just a straight line. We'll draw it next time when I see you. Okay? I will probably, my people, send you an assignment to work on with doing some reactions and figuring out the products of reactions. And I'll probably do more live streams with you next week. So that'll be the first time we'll meet again with a live stream. Okay? Thanks for joining me. Great participation today. And we'll see you next week, and look for an assignment on Google Classroom. Thanks. Have a good week. Bye-bye.